Welcome back. So I'm Sergio Conti, and I'm honored to introduce you Tristan Buckmaster from Courant Institute in New York. He's famous for his work on irregular and non-unique solutions to Euler and Navier-Stokes equations, for which he also got the Clyde Research Award 2019. Today is indeed going to talk about singularities in fluids, but through a slightly different viewpoint, self-similar analysis, computer-assisted proofs, and neural networks. Please, Tristan.
So first I'd like to say it's a really great honor to be invited to this wonderful conference, and it really brings me full circle because I was here as a master's student in 2009, I believe, under the supervision of Herbert Koch, and I think my time spent here really built my foundations of how I think about mathematics, and so Bonn, has a really dear place in my heart. So, I'd just like to thank you once again. So I'm going to talk more about techniques. So I don't want to talk about a specific result. I just want to talk about some techniques that are going into my current research that I think you might be interested in. So there's sort of three topics: self-similar analysis, computer-assisted proofs, and neural networks. And I'll link all three. So first are just some advertisements. Gonzalo Labora. So these are just two of the young collaborators that will be mentioned in this talk. So Gonzalo Labora is currently a PhD student at MIT, and Yonji Wang is a postdoc at Courant. The most famous problem is in the field of PDEs is the global existence or the singularity formation for the Navier-Stokes equation. So the problem is phrased as follows. So let's consider both equations. So we have the incompressible Euler equations or the Navier-Stokes equations. The Navier-Stokes equation is, of course, if you add this red term, this viscosity. And so this describes the velocity v, and you have this pressure P, and the open problem is for 3D Euler or Navier-Stokes. Does there exist a smooth initial data which will lead to the formation of a singularity in finite time? And I want to link these two problems together, meaning the problem for Euler and the problem for Navier-Stokes as well. So this was answered. So the problem for Euler was answered in the case of non-smooth initial data for Euler, C1 alpha initial data, and it was also recently proved by a wonderful result by Chen and Hao in 2019. In 2023 and this year, in the case where you have a cylindrical boundary. Okay, but the original problem is there's no boundary. So you just either considering the problem on R3 or the torus of the three-dimensional torus. Okay. So first, I want to talk about self-similar analysis, and you may have heard of self-similar. If you're in the field of PD, you may have heard of self-similar blow-up, but you've never sort of seen it visualized. What does it mean? What does self-similar singularity formation mean? So in the top picture, you will see the Burger's equation, which is probably the simplest nonlinear PDE that blows up in finite time, which I'll show in the next slide. And what happens is that at a certain time, you see an infinite gradient form. So the derivative of this graph above becomes infinite at the origin. Now, that's what the top picture is. So there's a picture of the evolution of the solution to the Burger's equation. So what is the second picture? The second picture is that red box. So the blue line is the same blue line in the top picture, except that red box in that top picture is the black box in the bottom picture. So if you zoom in on this image on the first picture, you get the image on the bottom picture. And then the natural question, what is this orange line? The orange line is that as you approach the singularity, if you zoom in and stretch everything in the right way, it converges on something very smooth. So you turned a problem which was to find something that becomes infinite, the gradient becomes infinite, to a problem where in these new coordinates, everything becomes smooth, and it actually converges to something that you know. So the first bit, yeah, so this is the picture to keep in mind. So when I talk about self-similar blow-up, I'm really just describing the behavior of the solution at the position and at the time of the blow-up. It doesn't describe the solution anyway in any neighborhood away from where the blow-up is actually occurring, or any. But as you approach this time of blow-up, it converges to something specific, and so I'll make that precise. So, this is elementary. PDE is this is the Burger's equation here. So you're given some initial data of the velocity, and you evolve it for some time. And it's very easy to solve the Burger's equation. This is why I give it as a toy problem, because you can solve it via characteristics. So you follow the characteristics given by the initial velocity, and then you have the velocity is constant along the characteristics. Remember, it's not the velocity that becomes singular, it's the gradient of the velocity. How do you see that the gradient of the velocity becomes infinite? Well, if you write the derivative along the characteristics, you get this equation here, which you can solve, and you can see this, that the derivative becomes infinite at time minus 1 over alpha if the initial velocity, so this is meant to be, this is not meant to be a derivative here, if u0 is initially alpha. So, this is, so trivial, you have that, in finite time, you have a singularity that can form. And so this is, the Burger's equation at least looks somewhat in the same realm as the Euler equation in terms of a fluid equation. So you can imagine there's some possibility of singularities forming, although there will be a different time. So how do I apply a self-similar analysis? So I've solved the Burger's equation exactly by following the characteristics, and everything looks very simple along the characteristics, but if you fix the frame, if you look at an Eulerian frame, then the behavior is a little bit more complicated. Okay, and so what self-similar analysis does is it allows you to extract the key information of the singularity at that point of the time that the singularity happens and at the point where that singularity occurs. So you have the same equation. Now you consider some ansatz, okay? You consider that u behaves like this. And what you've done here is you've said how it scales with time. And so the equation for capital U no longer has a time variable. But and what happens is you can solve this ODE and you end up solving this, this orange line. And this gives you an exact self-similar solution. This is a smooth solution. So where does the singularity come from? It comes in the singular nature of this coordinate transformation. At time equals 1, we have, it's a singular coordinate transformation. And so y is the coordinate, is this x-axis of this plot here. So this is the same thing as before. So what you see, so this is if you had an exact solution. Even if you don't have an exact solution, what you see is that the solution which is time-dependent will converge on this exact solution to self-similar Burger's equation. So that's self-similar analysis. In the case of the Burger's equation, we can solve, it's just an ODE, we can solve it explicitly. So you end up with this implicit solution here. And for this solution, remember, in the Millennium Prize, you want smooth solutions. You don't want solutions which have some regularity. You want it to be smooth, C infinity functions. So if you want the solution to be smooth, then you end up having some constraints on how you can choose this lambda. So lambda is the scaling, the self-similar scaling that you choose for these coordinates. So you have to pick lambda, and there's only certain choices of lambda you can make that lead to a smooth solution U. So what you get left with, you get left with these lambdas here. And I'll explain in a second, the most interesting one from a physical point of view is when I equals 0. This is the stable self-similar profile. It's the one that you observe. So the Burger's equation is this incredibly simple equation, but it actually arises in the limit of all sorts of other equations. So compressible Euler, so if you see a shock wave, the shock wave is at the limit. When the shock wave occurs, it is actually described by the Burger's equation. And there's lots of other equations like this. So if we pick this case when I equals 0, we end up with, we can actually solve this explicitly, and we get a formula for the self-similar velocity. You can plug this in and check that it's a solution. And then what do we mean by being stable? Well, we have to introduce sort of self-similar time, which is this S variable, which we define as, so T is the time that the singularity occurs. So in this case, a capital T is 1, so it's minus log 1 minus T. So all this does is, instead of having some time which goes up to 1, you move that time of the singularity to happen at time infinity. That's what this trick does. Now, if you do that, you get an evolution. Then the whole Burger's equation can be written in self-similar coordinates like this, where this is the main part. So this U bar is the exact solution, and U tilde is the difference. And what you see is that you can linearize around the exact solution, and you get some nonlinear terms, some error. And then you study this linear operator, and you see that this linear operator has the only positive real eigenvalues of this operator correspond to the symmetries of the Burger's equation. So in some sense, removing these symmetries removes the instabilities. And because it's just based on these symmetries, we call this is the stable solution. Now, if you take lambda so I equals 1, 2, 3, 4, 5, you get unstable eigenvalues. You get additional ones other than the ones to do with the symmetries. And these are unstable solutions. So this is my notion of stable and unstable. And what this means in reality is that if you transform everything in the right ways, and you have initial data that's close to the self-similar profile, then the self-similar profile will describe how the singularity occurs at the point of singularity and at the time of singularity, no matter if you perturb it a little bit or not. So that's what it means by stable. Okay, so that's part one of the talk. So the self-similar analysis is how I'm going to frame the problems. I'm going to frame everything in terms of self-similar coordinates. Later, I'll be talking about a numerical way of solving these equations. And I'll need a third ingredient, which kind of bridges pure mathematics with something that you obtain numerically. And that is via a computer-assisted proof. And so this is actually some code from a recent paper of ours. And I'll explain what I mean by computer-assisted proof. So now I will introduce implosion. So in implosion, we're considering the isentropic, spherical, symmetric, compressible Euler equations. If you consider radial symmetry, which is what happens in the case of implosion. So implosion is where So is where it's a singularity that occurs in a radius symmetric fashion. And of course, this was very much studied historically for kind of obvious reasons, but I won't get into that. So U is the velocity here, rho is the density. If we make some ansatz where we assume that the velocity and here's the sound speed, which is just related, is just a relation. It's just a form. It can be written in terms of the density. If we make a self-similar ansatz relating to the velocity and the sound speed, we end up reducing this complicated PDE into a much simpler autonomous ODE. Okay. And so the nice thing about autonomous ODEs is that you can study, or at least in the case of 2 dimensions, is you can study it in terms of phase portraits. So a recent result by Merl, Raphael, Rodiansky, and Seftel showed that for almost every adiabatic exponent greater than 1, so for context, if gamma equals 7 on 5, that would be what you'd assume for air. There exists countably infinite sequence of self-similar solutions to the isentropic Euler, which blow up, and in fact, the velocity and density become infinite at the origin. I won't go into what I mean by almost every. It's just there's some complex analysis in the proof, which means that they can't. They can show that this result holds for almost every gamma, but they can't show it holds for any specific gamma. The existence of non-smooth solutions to these equations was shown by Goodley in 42. And in that case, they were considering imploding shock waves. So shock wave, there's already a singularity that had already occurred. And then that propagates to an even more extreme singularity, which is the implosion. But no one had before proven the existence of implosion for smooth initial data. And this result received the Clay Research Award for this year. Okay. And what they also showed is that for a version of isentropic 3D compressible Navier-Stokes equation with constant viscosity, you also have implosion occurring. And the reason I want to bring up this result is this will kind of. I mentioned on the first slide that there's a link between the search for singularities for Euler to the search for singularities for Navier-Stokes. Now, in this case, there's a direct link between the singularities for compressible Euler and the singularities for compressible Navier-Stokes. And the basic idea is that you have to find a very... So remember before, I said that there was not just one self-similar solution to the Burger's equation. I said there was a whole family parameterized by I. So the same thing happens for compressible Euler. And what you want to do is you want to take a very high order, you want to take the very high order solution to Euler and use that to prove the singularity formation for Navier-Stokes. And so this is incredible. As you sort of take I to a very high number, you introduce a whole lot of instabilities. And so the solution is highly unstable. And so what this actually tells you is that if you try to do numerics, and people have done this for this compressible Navier-Stokes equation, and you just try to find an imploding solution to this equation, you'll never find it because it's unstable. You make a slight error, the singularity won't occur. And that's what actually numerically has been seen. And so the same thing you would expect for the incompressible Navier-Stokes equation. This is why we've never seen a numerical singularity for the Navier-Stokes equation, is because if one exists, it most definitely is highly unstable, and you would never observe it through simulation alone. But there are ways to find it. Okay. So there's two caveats to this result. One is that of this result. One is that the gammas, you take almost every gamma, and the other one is that for the Navier-Stokes result, they have to assume that the density decays in infinity. You don't really want to assume that because you don't want anything at infinity to play any role in the singularity formation. You want it to. So there's two things that you want to remove. And so the natural open problems were, do imploding solutions exist for all gamma, and can one construct imploding solutions in Navier-Stokes where the initial density is constant at infinity? And that's what we proved. And so this is a result of Cal Labora, Gomez Serrano, and myself. And for this proof, we used computed-assisted proof. Now, it's 130 pages long or something like that. So it's a long paper, and I'm not going to go through any details of this proof. All I want to show you is a technique used in the proof. Okay, so I said before, once you make this self-similar transformation, you end up with an autonomous ODE, which you can solve via a phase portrait. So what is the game? The game is to find an integral curve that connects P0, which is the origin, to P infinity, which represents infinite radius. So how do you do that? Well, you just draw a line and you're done. The only caveat is you're not allowed to cross this red line. So go ahead. Draw a curve from integral curve from P0 to P infinity, not allowed to cross this red line. You can't, of course. Except, okay, so now we can break the rules a little bit. You can cross this red line, but only at one point, and that's where, what is this red line? This red line is just the denominator here. So you don't want things to become infinite, you want a smooth solution to the self-similar equation. So you are not allowed to have the denominator vanishes. Except you are allowed to have it vanish when the numerator also vanishes. So you are allowed to cross this line as long as the two numerators vanish, which are the numerators are represented by the black and the green line. So you can cross at this point. So there's some curve which goes from P0 and it goes this way and it goes there, and that's basically the solution. The only thing is that this is an integral curve that connects the 2 points only for discrete choices of the self-similar parameter. Otherwise, it just doesn't connect. That's the game. Anyway, so I'm not going to go about how you prove it, but what I want to say is that because you have an autonomous ODE, a typical way that you show that an integral curve goes from point A to point B is you use barrier arguments. So a barrier is some curve in your state space where if you cross it, you can't return. Okay, and you can imagine you put up these barriers, you show that they're barriers, and you show that the curve must go from point A to point B. That's the basic idea. So let's make a completely artificial barrier problem. This has nothing to do with the actual original problem, and these are completely made-up polynomials that I came up with for the numerators and denominators. So let's consider this autonomous ODE, given above. Suppose we want to see that we have some curve given by R, and we want to show that this is a barrier to the ODE. Okay, so you can write down what this means. That this is just in terms of the perpendicular of the tangent derivative of the curve dotted with the ODE, with the right-hand side of the ODE. And you have to show this is less than or equal to 0. So if you multiply all the equations by the denominators, you end up with this equivalent problem. And the reason you can do this is that the denominators I chose were strictly positive. So you end up with this problem. Okay, what is this problem? This problem ends up being a 13th order polynomial condition. I learned a lot in Bonn, but they didn't show me how to prove that this 13th order polynomial is positive between 0 and 1. And that's what I want to show. Okay. So there's, so how do I show that? All I have to do for this proof is I have to show this 13th order polynomial is positive. Okay, so I'm going to make my life a lot simpler. I'm going to divide by minus t, and I'm left with a 12th order polynomial. Done. We can move on. Okay, so we have this 12th order polynomial, and we want to show it's positive in some range. So I can plot it. It's clearly positive. It's positive. You can see from the plot it's positive. I'm done, okay? Stop hassling me. Okay, so this is not a proof, unfortunately. Like, I can plot it. I'm sure everyone in this room is convinced, in my Mathematica skills or whatever I use to plot this, that this is positive. It's numerically stable, everything. But it's not a proof. So how do I turn this into a proof? So computer-assisted proof is in these problems that I'm thinking of, is the last stage of the proof where I'm proving something I already know is true. I'm just doing this last annoying step that I can't do by hand. So how do I prove that this polynomial is positive? Okay. So what I do is I replace my typical arithmetic operators acting on the real numbers with interval arithmetic operators. So I'm just going to give a sort of toy model of interval arithmetic. So instead of considering a number, I consider an interval. And I'm always going to consider, for this simple example, intervals with radii of powers of 2. Why would I do such a thing? Why would I restrict myself in such a way? Is because I think of this interval as like a point plus its error, okay? And I'm allowed to overestimate the error. That's fine. I just can't underestimate it. So when I add 5 plus or minus 2 to the minus 4 to 3 plus or minus 2 to the minus 7, I get 8 plus or minus 3 to the minus 3. Well, I've rounded up. Okay? And you can do the same thing with multiplication. And in this way, I can do arithmetic operations on a computer which give rigorous bounds. So I can say with confidence, I can say that with mathematical certainty, that when I add these two intervals together, it will be contained within some other interval. I'm not saying what interval it equals, I'm saying it's contained within some other interval. So I just always make sure I have enough room. I always overestimate the error, and this is how interval arithmetic works. It's a very, very simple idea, but in practice it's very powerful, and you can do a lot of things with this. And so I'm going to use this interval arithmetic for this very simple toy example that I gave before. And so this is just the polynomial, the same polynomial I said before. This is the 12th degree polynomial. And what I do is so when I plotted the polynomial, I evaluated the polynomial at set points. Instead of evaluating it at some points, I evaluate it on intervals. And I make sure the intervals overlap. Okay? And the intervals cover the whole closed interval from 0 to 1. Okay? And so if I do that, so I simply evaluate this polynomial at a bunch of intervals, and where the intervals are defined in terms of the number of divisions, then this is what I get. So if I take 10 divisions of the interval from 0 to 1, I get all these numbers with some error, okay? Now, the problem is when the error is larger than the value itself. Then I cannot guarantee that it is above 0. If the error is less than this positive number here, then I can guarantee that over that interval, the polynomial is positive. So it didn't work in the case of 10 divisions. So what do? I know it works because I'm proving something that I know is true. So I just make more divisions. And this is actually, key in our proof. We would divide things up, and Javier Gomez-Serrano, who did the computer-assisted proof part, he would get a bunch of things which would say true, 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 false, whatever. And then he would get one false. Okay, divide it up more. And then, we'd throw it at the cluster, and then eventually it would just tell us true, and then we could submit our paper. So that's how it works. And you don't have to just use this for polynomials. This can be used in a more complicated PD setting in order to prove in order to prove self-similar blow-up for much more complicated equations. But I won't go into that. So I just wanted, Okay, so the last topic I want to talk about is physics-informed neural networks. And so it was quite fortuitous this day. I was just walking along the beach, and I happened to see a mathematician writing on a blackboard while a singularity was forming in the ocean. So I took a photo. So what has this photo got to do with the title? Of course, it was generated using Firefly, Adobe Firefly. And the only thing that's real in this picture is the blackboard. Because neural networks are terrible at doing blackboards with mathematics on it. But the shadows are all wrong, and singularity is perfect, but yeah. Okay. So let me introduce this little how scenario. And this scenario was recently proved in a proof that used computer-assisted proof. So we consider the incompressible Euler equations either on the exterior or the interior of a cylinder, where you assume no-slip boundary conditions. And back in 2014, Liu Hao showed compelling numerical evidence that suggested asymptotic self-similar blow-up, and this was recently proved. The first paper was last year, and the computer-assisted proof paper was this year. So, okay, so I'm going to apply the ideas from the first section of this talk. So we're going to apply self-similar analysis to the 2D. We're going to apply self-similar analysis to the 2D Boussinesq problem because it turns out self-similar solutions to the 2D Boussinesq problem end up being the behavior of the 3D problem if you assume axisymmetry on this boundary. And what does that mean is that if you zoom in on the singularity forming, then you can imagine you have a cylinder, right, which is round. But as you zoom in, that becomes flat. And as that becomes flat, you lose the curvature in the equation, and you end up with this 2D Boussinesq equation. And you can make this precise, very precise on what the error is, where it's a 2D Boussinesq equation on the half plane. And so if you make this self-similar ansatz, so again you have this self-similar parameter lambda, which you don't know what it is, then you end up with these equations here. Okay, there's no time anymore, and you just have to solve these equations. And you also have to solve for what lambda is. And the idea is if you can construct a self-similar profile, then you can use this with a bunch of analysis and computer-assisted proof and so forth in order to prove blow-up for self-similar Euler. This is not the original problem. The original problem is without boundary. This is just the problem with cylinder. And so we constructed. So this is with the postdoc that I mentioned in the second slide, Wang, Lai, Gomez Serrano, and myself, we came up with a method which used physics-informed neural networks, which I'll explain in a second, in order to find solutions to these self-similar equations, and also to find the lambda. How much time do I have? Okay, good. Plenty of time. Okay, so what does it actually find? It finds some profile, and you get some error. And this is very much out of date. The error that we have now is much more. So the basic strategy is that you numerically find these self-similar profiles, and then you use some form of computer-assisted proof that shows that the linearized operator around this approximate solution has some stability modulo some eigenvalues, and for that you can prove that there exists an exact self-similar profile nearby. Something like that. So the devil is in the details. Okay, so what is this physically informed neural network? It's probably not what most of you imagine a neural network doing. Okay, so the easiest thing is to think of like, we're all aware of what a Fourier series is, at least we know that, okay? So a Fourier series is like a really simple one-layer neural network. So you can represent your any sort of function by a Fourier series, and so your input is x, and then you have all your neurons, which define the coefficients out the front of your Fourier series, and then it gives you your function u. Okay, so what are we using this neural network for? We're only using this neural network to represent a function. Okay, so we're not doing any fluid simulations and then fluid simulations and then training a neural network and then coming back and all this sort of stuff. What we're doing is actually we're training the neural network to find the precise function that solves these equations. So this is a simple it becomes a calculus of variation type problem. So you have to define some loss function. So what's the big difference, okay, from taking, say, a Fourier series from taking this neural network? So a neural network, a deep neural network, is you have several layers, okay? So this is like you have right at the highest layer, you have a sum of some linear sum of some activation function, which is your nonlinear function. It could be a sine function. In our case, it's normally taken as a tangent. And then you take the output of that function and you plug it into another linear combination of the function, and through these compositions, that you end up with a very complicated, highly non-unique representation of any given function. And if you try to solve, now you have all the coefficients, all these different weights and biases. If you try to solve for these weights and biases, the natural question is, why is it any better than this? It turns out that in many situations, for example, that a complicated solution, such as the solution to these self-similar equations as before, can be described with very few weights and biases. If you take this complicated representation. Of course, you have to design the representation such that you get a low-dimensional representation of the solution. And if you have a low-dimensional representation of the solution, it naturally makes it easier to solve the optimization problem. I mean, that's one possible interpretation of why it works. But in truth, we don't really know why deep neural networks work so well. But there are some general guidelines of why, heuristics of why it could work. Well, and we do know the fact that deep networks can very efficiently represent information. That's something we do know. Okay, so I'm going to go back to a simple equation, so the Kordoba-Fonteles equation. So it's given, it's a 1D equation. You have this omega, and then you have this velocity u, which is written in terms of the integral of the Hilbert transform of omega. And so compared to Berger's, it's a more complicated equation because it has this non-local operator. Okay, and so it's very hard to find, like, you can't. It would be very difficult to find an explicit solution to this equation. So if you assume the self-similar ansatz given above, then you end up with this self-similar equation, and then the problem is to find a solution to this self-similar equation. Actually, so this is dissipation that you add on, okay? And this goes back to the link between Euler and Navier-Stokes, is I want to study regimes where dissipation has no effect. You don't care about it. It becomes just some forcing term which decays exponentially in your convenient self-similar coordinates. So this dissipation term, once transformed into self-similar coordinates, becomes this red term here. And what you immediately see is this, if this alpha 1 plus lambda minus 1 is negative, then this whole term is decaying exponentially. And you can kind of treat it as a decaying forcing term. And so that means that if you can prove some stability of the problem without this term, then you can show an asymptotically self-similar solution to the equation with dissipation. And this is the same thing that's going on with the compressible Navier-Stokes equation and the Euler equation. So the reason we are able to construct asymptotically self-similar solutions to the compressible Navier-Stokes equation is we have to take certain scalings, which depend on our self-similar parameter lambda, such that the dissipation can be ignored. And normally this means that we have to take a highly unstable solution. So this is the caveat. And highly unstable solutions are harder to find. And certainly you would have no hope of finding this with a traditional numerical time-based scheme, because it's unstable. So an open problem is, so first of all, what do we know? We know that blow-up occurs if alpha, so alpha is this dissipation, fractional dissipation parameter. If alpha is between 0 and 1/2, we know blow-up occurs. We know we have well-posedness for alpha greater than 1, and we don't know anything in between. So if we pass to self-similar coordinates, this dissipative term, as I explained, can be treated as exponentially decaying forcing if we have this parameter. So if lambda is less than 1 over alpha minus 1. And so if we need to address the range which we don't know the answer to, we need to find solutions to the inviscid CCF without the dissipation for lambda less than 1. This is the neural network setup. So it's the same sort of thing. We have an input, we have our neural network. This gives our output omega and u. One thing neat about these neural networks is you can over-parameterize. You're free to over-parameterize equations, and in many cases that's a good thing, which is not the case for traditional methods. And it's very actually important how you parameterize your network. So the basic sort of process of finding these self-similar solutions is not just that we put in these equations to some into some Google search box and press enter, and we get the equation. We design some neural network which we think may work, and we press the button and it finds nonsense. And then we look at that nonsense and we see how do we, maybe that nonsense corresponds to some experience, some solution that grows at infinity or something wrong. And so we try to modify the cost function or the architecture of the network in order to focus it on finding the solution. And because we are kind of experts in this field, we know where to look. And it's a lot of back and forth until you finally find the solution. Once you find an approximate solution, you're almost there. Once you find the approximate solution, you can hone in and you can increase the accuracy and everything. But the first step is to find an approximate solution to your equations. And so this is what we do. And so the equation, the neural network itself spits out a smooth function. That's one thing to note. It's not like you do a discrete, you don't do finite difference methods. You get a smooth function that it outputs, and one nice thing is you can apply the chain rule to analytically differentiate this function. It's just a bunch of compositions of some very well-known function like tanh or sine or something like that, and you can get very accurate estimations on the error, and you can in fact bound the errors specifically. So that's what you do. And so this is two solutions that we found. And so the first is the stable solution, and this was actually already known in the literature. Now the first solution corresponds to a lambda which is greater than 1, so it can't answer this open problem. The second solution corresponds to some lambda less than 1, and one thing you see is that if you look at the linearized operator, you see that there's an extra unstable eigenvalue, which is as you predicted, and this is the thing, is that if you want to deal with these, like the Navier-Stokes equivalent problem, you probably have to find an incredibly unstable solution, which you can't find with traditional methods. And finally, this is the, okay, so this plot in the right-hand side is wrong. This is, I don't know why the slides does this, but so this is the initial training of the neural network. So here's U, and you can see how it trains over a number of iterations, and this is the error. And all I just wanted to point out is that it doesn't just smoothly converge on some solution. It does, there's a lot of funny wiggles that go along before it finds a solution. And this is after we've done a lot of massaging to know where to look. So you imagine the initial trainings when we were initially looking for the approximate solution, there was a whole lot of wiggling that occurs in the initial iterations before you find something smooth. So the training is very, the training finds something okay, and then you get, it suddenly drops down the loss. And it's not a clear like decay in the loss function, you get these sudden drops. Unfortunately, it won't, for some reason, because I'm using a web version of these slides, it won't show you this one. But anyway, I can, while we ask questions, I can show you that other one. So, thank you.